Hi, my name is Saul Neri, and I'm going to be talking about auroras. So let's start with this. Okay, the aurora is a natural phenomena that occurs when the particles contained in the solar wind interact and collide with some elements and particles suspended in the Earth's atmosphere. Okay, this is what causes it in a great resin, but I'm going to explain this in more detail in the next minutes. Okay. First, I wanna say something that I think it's pretty important and not everybody knows. The common term for describing this phenomena, at least in Mexico and northern hemisphere countries, is the aurora borealis. So, and this is a mistake actually, because aurora borealis only refers to the phenomena uh, occurring in the northern hemisphere, and it also occurs in the southern hemisphere. So, and there it's called aurora australis. So it's important to know the difference. It's not just aurora borealis. We have also aurora australis. Okay. This happens because we have two magnetic poles in the Earth caused by the magnetic field protecting us. So this is a diagram that shows the sun and how the solar wind that escapes from the sun reaches the Earth, and mainly the hemispheres, northern and southern. Okay, so this is like a big picture, a very good picture for understanding the idea. Okay, now, but the first question that arises from this is, how does these particles reach Earth? Why is the Earth magnetic field doing something wrong, or why isn't it protecting us? The answer is no. It's pretty effective actually, but as I was saying, in the poles it is weaker because of the shape of the magnetic field. This is normal, and this is nothing that should um, keep keep us awake in the night. Okay, so this is normal, and it's totally safe. But what kind of particles are those who reach Earth? Well, mainly they are electrons and protons that escape from the sun's atmosphere, and they escape because of two phenomena mainly: uh, sunspots, and are these red or black spots on the sun surface, and the coronal hole. Both are very similar, and both cause the escape from these particles. Basically, it's like a reduction in the temperature of the solar surface, and this causes like weakness of the sun's magnetic field. So all those particles are able to escape from sun surface and reach not just Earth, but actually every other planet. Okay, so mainly protons. Oh yeah, this is a proton diagram and an electron, and I'm going to explain what the hell is this and why the electron is just like a little circle. This is the standard model of elementary particles. We have like the basic parts of which our universe is made. We have the electron in here, and as we can see, here is the mass. The charge, the electric charge, we can see it like a -1. This is where the electron's negative charge comes from. Of course, this is a human convention, but we have the -1 charge, and this is something called spin. Okay, but it's not pretty important for our understanding right now. And maybe you have already noticed we cannot find the proton in this standard model. Why? It's actually pretty simple, because as in this diagram was shown, the proton, it's not an elementary particle. It is made of three different uh, smaller particles: an up quark, and down quark. Okay, here we have the quarks, and we see that the proton has two up quarks and one down. Fun fact, the plus one electric charge of the proton comes from the sum of the charges from 2 up and 1 down. Let's make this arithmetic operation. 2/3 plus 2/3 is 4/3 minus 1/3 is 1 plus 1. Okay, so we see where the plus 1 comes from and the minus 1. Here we have also the photon, that it's an electrical and a standard particle, an elementary particle. We see that it has no mass and no charge. This is why it can travel that fast, light fast, okay? And it has spin 1. This is, well, yeah. And here we have another important, they are all important, but here we have some interesting one, the Higgs boson. It became from the mainstream knowledge actually recently, because in the 2003, I don't remember, 2003 Nobel laureate of physics was awarded to Peter Higgs, who theorized the discovery of this particle. And in 2012, LHC, the Large Hadron Collider, found a particle that suited for all these different characteristics. And this is pretty interesting because the Higgs boson, it's who causes for all these other different particles to have mass. It creates like a field that permeates every single part of space, and some particles interact with this field and causes them to have mass and to not travel at the speed of light. It's like a break. This field stops them from traveling that fast. So that's why the particles that do not have mass are the ones who can travel at the speed of light. Yeah, the photon is not the only one. We have the gluon, and we have that's it. Those are the ones who travel that fast. That is why, actually. And we have the muon and tau, different particles. So here we have a diagram of the magnetic field of the Earth. We have a north pole and south pole, and we can see that it has a slope. It's not totally vertical. Well, this is partly true, partly false, because it's proven that with time this field changes. So right now we have this north pole, as we may call it, in this hemisphere, and the south pole, but it will eventually change, and it has already changed in the past. So I don't know, maybe in the future we have something like here, who knows, okay? But it changes. Yeah. The second important question to answer from this phenomena is, how are the color formed? This is a little bit more complicated because it deals with the interactions between the particles, but mainly we can explain it as this. If the solar wind interacts with oxygen, it will create red and green colors, and if it interacts with nitrogen, it will create the blue color. Okay, so we can see red, it's at highest altitudes, it excites atomic oxygen, and it emits this wavelength that corresponds to the red visible light. Okay, this is oxygen at higher altitudes. Now with the green, that it's like the most common color for these auroras, occurs with the collision between the particles and the oxygen at lower altitudes that are much more frequent than the red particles, that the red color. Okay, so it emits this wavelength that it's green. Okay, now we have the blue, that it's at yet lower altitudes where oxygen is not abundant. So we have nitrogen, that it's actually like the most part of our atmosphere. and it creates this wavelength, which is blue. Okay. Also, we have yellow and pink. They are much more weird. There's a mixture of green and blue and red, and actually every color is theoretically possible, but we need to have the precise conditions in order to achieve them. Okay. So we have, of course, a similar question that arises from this. It's why is the sky blue? Okay, so it's a similar question to this, and we can answer it using the Tyndall effect. The Tyndall effect describes the scattering of colors when when some particles collide with our atmosphere. As I said in the past, nitrogen is the most common element in our atmosphere. So here we have the nitrogen. It creates the blue wavelength. So in the atmosphere, the most common element is nitrogen, and that is why we see our sky blue. But when the sun is at the horizon, it travels a longer distance to our eyes, so it has more time to scatter, so it gets to the red, yellow, to the red wavelengths. Okay, and so, as I was saying, the Tyndall effect describes light scattering by particles in a colloid or colloid. It's like a suspension, or else particles in a very fine suspension. Okay. The intensity of the scattered light depends on the fourth power of the frequency. So blue light is scattered much more strongly than red light. Actually, this fourth power is very important because if we plot the x to the fourth power, we will see that it's an exponential, of course, and it has a pretty high slope. It acquires a close to one slope pretty fast. Okay, so when the blue wavelength that is actually smaller than the red one, we rise it to the fourth power, we see that it will be much more scattered, much less scattered. So the red is more scattered, the blue is less scattered, and the red is more scattered, so we see more blue. Okay, a fun experiment to do this is to suspend some flour on milk and light it and put some light into it. We will see that the suspended flour in the milk will acquire like a blue color, a blue tone. Okay. Also, we can see this in the smoke coming out of the engines of motorcycles, cars, and every single engine vehicle, because it has nitrogen and different elements resulting from the combustion equation. Okay. Also, I saw a video of this phenomena where the smoke coming out from a cigarette, you can see it actually white when you see it with light. Okay, but when you smoke it and retain it in your lungs for a long period of time, the smoke will absorb some humidity from your lungs, so when it comes out, it will have water particles suspended into the smoke. Okay, so when you blow and take the smoke out, it will be some little water droplets on the smoke, and it will acquire a more blue tonality because of this effect. Actually, exactly. Okay. Here are my references, and I would like to finish this by just giving you some geography classes, by telling you where, if you want to see this phenomena, where is it easier to see. Of course, it's easier to see at higher or lower latitudes. I'm sorry, close to the North Pole or South Pole, But people actually travel to Alaska and the northern parts of Canada to see. It's where it's easier, but also in the Scandinavian countries like Sweden, Norway, Finland, Denmark, all of these countries, it's actually pretty easy and common to see them. Um, but it has been reported to be seen at lower latitudes, like in even Scotland, I think. Yeah, when the solar activity is pretty strong, it's actually possible to see them from southern or northern, if we are in the southern hemisphere, latitudes. Um, that's it.